Welcome learners for the UGC series of lectures on laser physics. In the earlier lecture, just previous lecture, I was telling you that lasers that are commonly available in the market are mostly oscillators. They generate electromagnetic wave, coherent electromagnetic wave of infrared, visible or ultraviolet. These are the most common lasers. They are all oscillators, but there are certain occasions where the lasers can be amplifiers also. In this particular lecture, we shall give more emphasis for amplified lasers or lasers which act as amplifier. To understand this one, let me go back a little so that we will recollect what is the importance, what is optical gain, what is the importance of optical gain to distinguish a laser oscillator from laser amplifier. Now, let us see. Now, go back to the same resonator, laser, oscillator. Let me quickly repeat. There is a small chamber, rectangular chamber where you have some gas, liquid or whatever solid. Then there is a pump which supplies energy. The pump will be optical or electrical mostly. Then there are two mirrors at the far sides in the z axis which are capable of reflecting light of only one narrow bandwidth. One of them will be 100% reflecting, the other will be about 80% or 90% reflecting. These are the general configuration of any laser oscillator. Then this particular equation already I have explained, still it is worth repeating because this is a crucial point. In this case, as I told you, I have supplied energy, enormous energy, so that there is a population inversion inside the medium. Then you will have plenty of spontaneous photons in all direction. Out of that, only few of them will go in the plus z and minus z axis. They go back forth and back and forth, they become stimulated photons. Now, we are going to start with the stimulated photons alone. If n is the number of photons that start at some arbitrary point z1, it would have grown up as n exponential gamma L z1. That is how it have grown intensity. Then it falls on the mirror R1, get reflected. R1 represents reflection coefficient of the mirror R1. That means, if the R1 is 0.9, if 100 photons fall on the mirror R1, only 90 photons will come back, 10 photons will be lost either as a useful output or as a scattered loss. Then imagine this number of photons, that is, look at the next part of this equation, n exponential gamma L z times L1. This is the number of photons which will be coming back in the minus z direction. They pass through through the inverted medium, and then when they reach and fall on the mirror R2, they would have grown as exponential gamma L, where L is the full length of the active medium. That would be the number of photons which fall like this on the mirror R2. Next, this mirror again reflects. It has a reflectivity of R2. Imagine that is 100% reflecting, but let us say put eventually or generally as R2. Then after reflection from the mirror, what goes back in the same positive z direction will be n exponential gamma L z times R1 times exponential gamma L, where L represents the active length of the medium, times R2. where R2 represents the reflection coefficient of this mirror. Next, then when this signal reaches Z1, it would have grown up, the number of photons would have grown up as exponential gamma LZ1. You can do this calculation, very simple, exponential gamma LZ1. That means LZ1, do not get confused, LZ1 represents the small length from L is equal to 0 to Z1 point, Z1. Then R1, you can easily understand reflectivity of mirror R1, exponential gamma L is a gain coefficient, L is the length of the whole medium, multiply, you got it. Then R2 represents the reflectivity, then again since the light goes back, it would have grown as exponential gamma ZL1, that ZL1 is a small distance between Z is equal to 0 and Z is equal to 1. All these put together will be the final resultant light that has started from here, gone up and come back to this one. Now, suppose this quantity is equal to n, that means after one round trip, this n on the right hand side is equal to the whole number of photons given on the left side. This means the laser is under a steady state condition, because a certain amount of light has been taken out as a useful output. Under this condition, you will have a steady state oscillation process. That is how any oscillator works. This is all I have explained. Now, let us go back to the same thing. In the steady state condition, whatever I have written is a long equation. If you simplify, you will get exponential 2 gamma L times R1 R2 equals to 1. This simple crisp equation represents the threshold condition and the steady state condition for most of the CW lasers. I say most because there are certain design modification you can always play around, but most of the marketed lasers, they obey this law, this specific condition. Here gamma represents the gain coefficient. I compare this one to the business. The same way, in a business, what do you do, what do you expect, what you want in a business is a gain. That is, you put so much money, let us say 10 lakhs of rupees, and then so much efforts, so much time, all put together is the input, and then you get certain output. If the output is equivalent to, not equal, because you cannot quantify easily the efforts you put it, the time you put it. You can quantify the money you put it, but the efforts and your ambition, all these put together, we say total efforts input is equal to total output, then this business will continue without any stop. This is the essential condition, threshold condition. You can, if you have a very high gain, you can get very high power, but you can have a very high power only for a short time. So, this is the steady state condition. This is the condition for most of the commonly available marketed CW lasers. When I switch on a helium laser, if I get 5 milliwatt, if I get 5 milliwatt in the morning, I will get the same 5 milliwatt in the evening also, even if I run it continuously. Remember, even if I switch on and work with the laser for 3 hours, 6 hours, I would be able to get same 5 milliwatt from the morning to evening. This is the steady state condition, or this is the minimum threshold condition. Both are equal for a CW laser. This story is different for pulse laser, which we shall see later. The most important point at this point is the coefficient gamma, which is called the gain coefficient. This is something like a profit in a business. Let us see. In this case, immediately you can see, go back to this one, there are variety of lasers, helium laser, carbon dioxide laser, neodymium laser, every one of them. Suppose the Heine laser, the gain coefficient is very small, very small, then you need the mirrors should be, I go back to this equation, yes, you can look at this equation. Imagine if gamma is small, this is a typical example for Heine laser or a CO2 laser, gamma is small. To make this condition satisfactory, you need only this. There are, you can make L's equal to high, long, R1, R2 also very high, R1 should be 100%, or in terms of coefficient we say R1 is 1, R2 should be 0.9, that is 90%. Only then this will satisfy the condition. Because of this one, for a CW helium laser, you need a laser of about 1 meter length, and then it will be a small diameter. You will have two mirrors incorporated inside, one will be 100%, this will be 95%. Only then the Heine laser will work. On the other hand, if the optical gain is high, like a dye laser or your semiconductor laser, look at this one. Gamma is very high. Since gamma is very high, L can be even small, R1, R2 can be very small. Even then the condition is satisfied, because I repeat, because of the single most reason, gamma is very high. It is something like a business I do for one day or 1 month and make a lot of money and go. Sometimes people do such a business occasionally, maybe for in share market they invest money, within a month they get a lot of money and then they go, they are happy with that one. This is all rare. In a semiconductor laser, gamma is really high. Now, let us go to the next condition. I have given two extreme cases, a helium ion laser which is about 1 meter length, a diode laser which is about, in fact, in a diode laser the size of a laser is about 1 millimeter, that is all. Now, let us look at another condition, a dye laser. The dye laser has a much higher gain. Then what would happen is, even when there is no mirror at all, it will produce amplification. In one single transit, it can come out as a very coherent light with very high degree of coherence, and that kind of light is called amplified spontaneous emission. Why we call it as amplified spontaneous emission? In a dye laser, you take, I go back to the example, imagine this rectangle tube contains a dye solution like rhodamine, like fluorescein. These are all commonly available dyes. You must have heard about safranin, which is used for geyser sweet, I like it. In that you have safranin, you see you will have a bright orange color, that is due to a fluorescent material called safranin in that chemical, which is commonly used for your food. I told you the sweet saffron. Now, if I purify it, make it really good quality, I can put it here in this rectangular tube. So, it becomes a dye solution. It is easily dissolvable in water and alcohol. I can keep it here. Then I shine intense light either by the flash lamp or from a laser. If I shine light using a flash lamp, you can have population inversion all along the z direction. If the population inverse is really high, optical gain is also very high, then under that condition what would happen is, the spontaneous emission generated everywhere will be lost. The spontaneous emission generated only in this direction will produce stimulated emission, very high stimulated emission, and by the time it comes out, even without the resonator mirrors, you will have a coherent light which will be a cone of directional light of a very narrow bandwidth of frequency. Where did it come? This coherent light started as a spontaneous emission, got amplified step by step, but it got amplified very high, then it comes out as a coherent light. This is called amplified spontaneous emission. That means, this particular kind of medium is capable of achieving high population inversion, producing high optical gain. So, in one transit it becomes a very good quality laser. There are people like you must be, perhaps you must have heard about Macaulay. Macaulay was a horrible prodigy. He usually memorized everything easily, and then he will go play and make a hell of problem for his mother. Then this, I am not joking, this is a real life of Lord Macaulay. His mother would say, go and read Bible 20 pages and then only I will allow you to play with your toy. He will go upstairs, take Bible, before she goes and washes his dish, he would have memorized 20 pages of Bible and come and just he will repeat and then he will go to the game. Because in one single reading he is capable of absorbing the every line, every word of Bible. He is such a child prodigy. There are people like that. We know Ramanujam, he could just look at it, he knows the whole follow steps which we struggle for years together. He could absorb, gather up, do the calculation, repeat, finish that one. That is a kind of high level of optical gain these few lasers have. For them, the whole effect as coming as optical amplified spontaneous emission. The only reason is they are high gain lasers. For them, the mirrors are not important, they do not have to be 1 meter, they can be small, 1 centimeter length. Remember, Heaney laser needs about minimum 30 centimeter, a dye laser needs only 2 millimeter, even then it will work. These are kind of special type of lasers. Some of the most common, most respected mirrorless lasers are sometimes called amplified spontaneous emission lasers, are excimer lasers, nitrogen lasers, dye lasers, copper vapor laser or gold vapor laser, and variety of semiconductor lasers. They are special, we say they are a class apart, that is a league apart. In one single transit of population inversion, they would be able to produce laser action. Okay. But the point is, all these are pulse lasers, all these high gain lasers, all these crazy lasers like excimer, nitrogen laser, they are not still continuously, they are pulse laser, you will get pulse by pulse. Whether this particular laser will work as a high gain ASE mode or the conventional resonator based mode, both are determined by the gain coefficient. Compare Macaulay, Ramanujan class apart, people like me is another story. We are low gain people, so I have to repeat so many times, then only something will go into my head. For Macaulay or Ramanujan, in one single transit they would grasp the whole idea. So, let us say there are two types of lasers, low gain lasers, high gain lasers. Some of the examples of low gain lasers are neodymium laser, the gain is 0.033 per centimeter, helium neon laser even less, for argon laser again very low. Examples for high gain lasers are what we call ASE lasers are, dye laser has a high gain of 0.5, just compare neodymium laser and on the right side dye laser 0.5. Argon fluoride laser is 0.17. Conjugated polymer lasers is about 2.3, it is a terrific laser which I love it. And then copper vapor laser. Now, all those on the right hand side are high gain lasers. I can say Macaulay laser, Ramanujan lasers. All those on this left hand side are ordinary lasers like me. Now, how they behave, I want to show the difference. This particular picture is very interesting. If you look at carefully, we have a rectangular medium in which we have certain gas. It may be a nitrogen gas or a dye solution or a semiconductor. It can be anything. You supply power. For nitrogen gas, you have to supply power by electrical discharge. For dye solution, you have to supply power, extra energy only by optical pumping. So, generally I put it as pump. Then what would happen is, the photons which are generated within as a spontaneous photon get amplified all along, and when they come out in this direction, they have extraordinarily small divergence, about 10 milliradian. So, you will get amplified spontaneous emission in this side. Whatever the story I told you for this side is true for this side also, because there is no resonator mirrors. We remove both sides. You take the medium, put the sample, maybe nitrogen gas or a dye solution, pump it. Usually it will be a transverse pumping. You can do longitudinal pumping also, easily transverse pumping. Then all this, for example, for nitrogen laser, for about a meter, you can produce a population inversion over a length of 1 meter length by producing excitation across. So, this is called transversely excited nitrogen laser. There are transversely excited carbon dioxide also is there. Let us focus on this one. Then the spontaneous emission produced at this point will get amplified, and the light that comes out in one single transit becomes amplified. It comes as a coherent like this side. Same way the light spontaneous emission starting from this side gets amplified this direction. Remember, only in this direction you will get ASE, this side, not in this direction, because in this direction there is no population inversion. There will be population inversion only for a small length. That length may not be sufficient to produce stimulated emission or a coherent radiation. So, most of the time the amplified spontaneous emission is confined to plus z direction or minus z direction. What we usually do, we put one mirror, so you reflect it. So, the light that comes out will get additional amplification, and in this direction you will get a very strong amplified spontaneous emission, which is almost comparable in terms of coherence to the conventional laser like a CO2 laser or a neodymium laser. Why at all you bother all this one? For certain types of gases, for certain type of medium, they work mostly in amplified spontaneous emission mode. One such example is the excimer laser. One of the excimer laser is the one most purchased in the medical field. They use it for refractive correction of eye cornea. It is a very famous laser, very popular laser, and most of the ophthalmologists are very happy to employ this one because it easily brings a lot of money for them. It is a very successful business. Okay. Let me compare the two types of laser. Conventional lasers like helium neon, CO2, argon ion, neodymium laser, all of them you will see one after another. They are all low gain lasers, and they can be working in a CW mode, continuous working mode, or in pulsed mode. When you work some of these lasers like nitrogen laser or excimer laser or even dye laser, they will be working only as a pulsed mode, and they are all amplified spontaneous emission mode lasers. The divergence is about milliradian, the spectral width will be 0.5 nanometer for ASE lasers. For a conventional lasers, the divergence can be as small as 0.3 milliradian, 10 times or even 5 times less, and the spectral width also can be very small. That means, compared to the conventional laser, the coherence property of ASE mode laser is poor, but it is much better than ordinary light, which is emitting radiation in a big bandwidth in all 4 pi radian. That means, there are certain applications where helium ion laser is the best, and there are another kind of application where excimer laser is reigning supreme. These are called ASE laser, these are called conventional lasers. I would stop with this one. The ASE lasers are true examples of amplified spontaneous emission. The spontaneous emission signal generated within gets amplified. So, these are the real lasers. All the conventional lasers are losers, because they are the laser oscillators by stimulated emission of radiation. But remember, we do not want to call a laser a loser, we do not want to feel a loser. So, unless you are all familiar with all these subtleties, we call all of them are lasers. Only difference is conventional lasers are very coherent, but power is low. On the other hand, ASE lasers are very high power, less coherent than the conventional lasers, but the power output is very high. Both have very important application, different field. Okay, in this particular lecture, I have been able to show you the difference between laser oscillator and laser amplifiers. All these are determined by the inherent property of the medium and also the pumping. Remember, it is a medium which determines which can be pumped by optical excitation or electrical excitation. There are so many other excitations. They are all determined essentially by the medium. Second point is, it is the medium which determines whether it is going to be a high gain laser or a low gain lasers. Now, once you have got both this, you can use it in amplified spontaneous emission mode or in the conventional laser mode. That is the reason why we study the property of the medium very thoroughly to understand the inherent limitations, inherent advantage of each of them. Based on this, we design the pumping. Based on this, we design the kind of laser. Based on this, we choose different application. Now, you have a wide range of lasers. Some of them are very high power lasers which are capable of burning a satellite, or there are other lasers which are toy, which the child can, 5 years old child can play with this one. You must have seen small, which we have shown in the beginning, toy or a very good lasers which are available for 100 rupees. That is all a very good quality laser, remember, they are all available. So, there is a wide range depending upon the necessity requirement. You must make a proper selection of the laser and the proper design of the medium and pump, and also the resonator capabilities. Thank you very much.